Okay, I got the info that recording is in progress. So for the sake of the recording, we'll continue the considerations from the previous meeting, and we will shift from theory to some practical applications and try to get a feed for some data. So let me share screen. Okay, so I think you now see my screen.
Yes, we do.
And then I will open some data which we actually recently collected. Just a moment. Okay, so there are data for some Haribo gels. You see, we took 6 different gels and we performed the field cycling studies at 2 temperatures. Yeah, it was at the room temperature, and here the temperature was higher. And as you can see, there are some differences at room temperature between different gels. They manifest themselves mainly in the low field range. And the differences are much higher when we go up with temperature. Now, okay, maybe this is not a very exciting thing. However, definitely we can try to analyze some of the data. So let me try. So I will copy this thing here. And let me edit this figure. So I will have only one data set, whichever one we need. Okay. So I'm switching off. I will use, by the way, origin software here. Okay. So I have only one data set. And now is the question, what should I say about this data set? You see, the first thing is that the relaxation is very, very fast. It's like here it reaches almost 2, 3, 4, 5,000, which was the relaxation rate, I mean 5,000 reciprocal seconds, which is a kind of miracle that we're even able to measure that, because usually the limit of the relaxometer is like here, but it depends on several conditions. And actually in the high field range, it's like the relaxation is still pretty fast, because even the last point is like almost 40. And you have to keep in mind that actually the relaxation rate for pure water in bulk, is like 0.5. So somewhere much below. So even looking at those values, one can draw some very important conclusions from that it is highly unlikely that we just look at water dynamics. I mean, okay, when one thinks about water, one usually says, and I suppose this is indeed true, at least a lot of experiments show that usually one has something like 2 pools of water or even more in the sum. And usually 1 pool of water behaves from the point of view of dynamics more or less like bulk water. Maybe the dynamics is somewhat slower, but let's say not much. And there's a second fraction of water, which usually the dynamics of which slows down very, very much by order of magnitudes compared to bulk water. However, even so, even in such case, I could imagine that the relaxation rate would reach, I don't know, 100, but not the order of thousands. So this is a kind of very interesting thing, because probably we do not look at water dynamics here. However, on the other hand, we really do not know what we are looking at, and we really do not know how to start the analysis. One can do, in such a case, a very simple thing. I don't know whether it will work. I did not try it before, I have to confess. I tried before some other things. However, anyway, let me put it like that. I have completely unknown data. And you remember, as I told you, that the simplest expression for relaxation rate is something like that. I will write it here quickly. So it's the relaxation rate. Yeah, it's the relaxation rate as a function of the resonance frequency. So the resonance frequency is omega, and it is like dipole constant, dipolar relaxation constant, which somehow includes information about distances between interacting hydrogen nuclei and some information about the fraction of band water in case we deal with water, what is not really necessarily the case here, times a very simple combination of Lorentzian spectral densities. This is something what I suppose you remember. So here we had a correlation time. And here we had such a quantity. Sorry for writing it now, but maybe you write it in this way. You will also like it because we'll be proceeding quite slowly, and there will be time to get some insight into that. And actually, I'm almost finished. Squared plus 4 times Ctrl+C, copy, paste, and here you have factor 2. So this is the simplest expression for a relaxation process, and it assumes that the correlation function is single exponential, so the Fourier transform is just Lorentzian. And tau c is a kind of time scale of the motion. So this is the simplest expression. But of course, for sure, as the experiment is performed over a broad range of frequencies, for sure we see here more than a single dynamical process. I can absolutely assure you that actually there's no way to reproduce the data using this kind of expression. But maybe one can do the following thing. Okay, I know nothing, in fact, about the sample. I know nothing about what the data represent. But after all, if the relaxation data cover 4 orders of magnitude, I could make a kind of decomposition. I would even call it parametrization. It is not yet going very deeply into the mechanism of motion, but I could at least do the following thing. I can decompose the relaxation rates into such contributions. The point is how many. Of course, the trick is that if I decompose it into 10 contributions, of course I will get perfect fit. But it does not make much sense. I will have very large numbers of parameters and I can fit everything. I would say that as we have 4 orders of magnitude, I would say that 3 contributions is maximum. So we can adjust somewhat this expression in such a way, so we can say, okay, let it be like that. A dipole constant, or the polar relaxation constant, corresponding to a kind of slow dynamics. Whatever slow dynamics means in this case, I will use the index S. So this will be our first contribution. Plus, let me add next contributions. So a kind of intermediate motion on an intermediate time scale. So I will put I here. I will put I here. Plus, again, a kind of fast contribution. So I will call it fast. Okay. Fast and fast. And just in case there are some impurities in the sample, or I still can catch at high magnetic fields, high frequencies, contribution from bulk water, I will add a frequency independent term, which I can always put to 0 if I like. So in principle, one could say that my first attempt could be to try to reproduce the data in such a way. Whether I will get a fit, this is a different story, and we'll try in a second. I did not try it before because I fitted something else. However, if we do, one can always say, okay, it does not have much meaning. However, in the worst case, I can say that actually the molecules in the sample are involved in free dynamical processes, which are characterized by something like a mean time scale, which corresponds to the correlation time tau slow, tau intermediate, and tau fast. So it gives me a kind of a picture of the motion, although I know nothing about the mechanism. I mean, if I, for instance, determine those parameters, okay, I can say it seems like there are 3 pools of hydrogen nuclei which are involved in dynamics on this time scale, that time scale, and that time scale. But I still do not know which hydrogen atoms they are and how the motion in fact looks like. But at least I know something. So I would try to keep it as the first step. Actually, this is also that people quite often, we discussed it recently, assume that that dynamics is heterogeneous. So it is a kind of distribution of the correlation times. Well, whether this is true, here we do not make any assumptions, yeah? You could treat the decomposition as a kind of distribution, because definitely if you say that there are 3 contributions to the relaxation, it means at least 3 kinds of dynamics, but it comes in a natural way. You do not assume that there is a distribution of correlation time following some Gaussian law or something like that. You just get the information in a kind of natural way. Okay, it seems that there is a pool of hydrogen nuclei which undergo a dynamical process which is completely unknown, but is characterized by a correlation time like tau s. There is also another pool of hydrogen atoms. Maybe it's the same one, actually maybe not, because the same nuclei can be involved into dynamical processes. And the time scale of this motion is like that. And let's say to complete the picture, there's also a faster motion. And it is characterized more or less by such a time constant. So at least it's first attempt to get a kind of quantitative information. So let us try. As I said, I never did that before for this particular sample.
Danuta, can I ask a question?
Sure.
So here you have listed the different contributions and you are still listing it as R1. Does it mean like it is the first component described by 3 contribution, or
it's
is it
just the relaxation rate as a function of frequency?
Oh, okay.
Yeah,
it's
so
like
whenever you take it,
okay.
At some frequencies, one contribution will be more important, at another frequency, another one. But let us see whether we'll get the fit.
Okay.
Then, but as I said, I do not know whether we will. But let us try. Okay. So analysis. This is nonlinear fitting. You can use whatever tool you like, but I just decided to demonstrate it using origin because many people do. So of course, nonlinear curve fit. Let us open the dialog. And I have to say that I prepared myself a little bit here. So I have a function which unfortunately has a very unhappy name, namely cancer analysis, but whatever, we can change the name. Actually, it stems from the fact that at the beginning, we try to see whether one can parameterize some other data in this way. However, here you have the code. So this is what you have here. Those 3 contributions. So this is, let's say, slow, intermediate, and fast. But of course, you cannot assume that actually this is the slowest one, this is the fastest one. We have just 3 contributions to the relaxation, plus a kind of frequency-independent term. And what is important here, you have here this factor 6.28, which is nothing else like 2 pi. Because you should remember that we have omega, not so the frequency in angular frequency units in this expression. This is a kind of very common mistake that people just forget to put here 2 pi, yeah, in this expression. So let us see what happens. Parameters. Well, I really do not know. Let me put something like a typical value, power 7. Then let's say that the longest time is -6. As I have completely no idea what will happen, I just use for the dipolar relaxation constant just something. So the intermediate process, let it be something somewhat slower. So let's say -7. But as I said, I know nothing. I'm just trying. And the fastest one, -8. And I don't know whether I need the factor A or not. I have completely not idea what happens. There's the simplex procedure, which is here often used. Well, I got something. And of course, the something does not make any sense. And especially as I got here even some negative values, and especially I got 0, I got very negative values for A. So let me put it 0 at this moment and try again. Okay, it still does not work well. I have here some negative values. Actually, I would say that it does not matter, but we could also play the game a little bit differently. Namely, I can do something else, namely I can put here like 30, because this is the last point. I can try to, because definitely I have here significant differences. So if I look at the value of this last point, which is like between 30 and 40, I can be sure that if I add a frequency independent term, which is of this order, I should not get such discrepancies. So let me check what happens now. Oh, you see, I got quite nice fit, except of the fact that those two values are negative. Actually, I would say that it does not matter, although it might be very disturbing from you. Why it does not matter? Look at this expression here. If this value, if the correlation time is negative, it's squared here anyway. So it does not matter. It's positive. Yeah, squared of everything is positive. If this value is negative, but this one is also negative, the product will be positive. So in fact, it's nothing else like a mathematical artifact, but I will make it positive for the sake of the fit. Yeah, nothing happened. Let us fit the data. So you see, I got a set of parameters and I got a very nice fit. Yeah. So I was able to reproduce the data. And in principle, as you can see, I have those dipolar relaxation constants and the corresponding correlation times here. So it's indeed like -6, -7, -8, but of course it got adjusted. You see the trick sometimes is just really to fix this frequency independent term, because fits usually have this behave in such a way so as the values here are larger. The software tends to reproduce this part of the data, but not this one. But now we can come to the point which Messi raised, actually which data I really reproduce in which range. Okay, so it's important to keep this in mind. I will make a note for myself so I can do such a thing. The first contribution, the C1 and T1, it's like 1.65 E8, 2.33 -6. Okay, so I will do something again. Let me make such a thing. Analysis. Fitting, again, nonlinear curve fit, open dialog, and I will show you something. This is this thing, and parameters. So now let us proceed in this way. This is 0, this is 0, this is 0. I will draw only one contribution. This is 0, and those are fixed. And let me draw this first contribution. So it's 1.465 power 8. And this one is 2.33 -6 and I will make them fixed as well. Yeah. So, sorry, I have to do it again. Analysis. So I have to do it again. So I want to plot the first term. So I put to 0 all other terms and fix them. And I want to have only the first one. So it's 1.4658 and 2.43 minus 6. Okay, and this is of no importance. This is also, I can write here, slow dynamics. And here you have the contribution to the relaxation rate associated with slow dynamics. So you have this first contribution with this longest correlation time. Let me proceed. I will do the same. So now this is 0. This is 0. The first one is 0. Of course, this factor is 0. The third contribution is 0. And only the second one is important. And the second one is like 1.9. So 1.9. And the correlation time is 4.835. 4.835 minus 7. I'm just copying this set of values, and they also should be constant. Well, I don't know actually what happened. For some reasons, they understood nothing.
Hocam, we couldn't add the T2 value.
Yes, I know. I have to do it again, sorry. Yeah, but maybe it's not so bad. Last used. Parameters. So this is 0, this is 0. This is 0, this is 0, and this is 0. And here is 1.9. And the T2, it was 4.8 minus 7. 4.8. And yeah, and fit. Okay, this table is not important. However, here you have the second. So this will be now. Let me make it like that. Then make it blue. And this will give me intermediate dynamics. So this is the intermediate contribution. You see, as the correlation time is shorter, the curves bends down at higher frequencies. And now I can make eventually the last one. So this one is 0, this one is 0, this one is 0, this one is 0. The last factor is also 0. And what I have here, C3 is 1.21, 1.21, and T3, 533, 533 minus 8. Yeah. So this is also not important. Let me make it. So this is fast dynamics. And eventually, what is worth to do, let me make such a thing, is this factor, 30. So I will do it in this way. Workbook, column, add new column, column, set column values. It is 30. And this is window graph. Insert plot to layer line. Where's this thing? I have to find it. I suppose it's this one. Yes. So I have 30 here, of course. I have to change that. Yeah, but I have it here. Let me make it here. And enlarge it. Okay. And here I have frequency. Independent factor, which might reproduce a very fast dynamics. Yeah. And in this way, we achieved a kind of parameterization of the data. So indeed, we can say that the data, whatever one says, can be reproduced in terms of such three processes. Whether this is good or bad is a completely different story, yeah? But one can do that. So this is what people sometimes call a model-free fitting or something like that, because it does not say much about the data, but it gives at least a kind of quantitative analysis. And one can, for instance, try to compare that with temperature. What I could do, for instance, I will copy the data here. Just for a second. I have it here, and we can do something else. We can try to use the data for higher temperature, because after all, what we know, with temperature, the structure does not change, and dynamics should become faster. I mean, this is what we expect, roughly speaking. So we can see whether this model will survive this concept and what happens if we take the data at higher temperature. So this is something what we have here. Yeah. What happens if we take data at higher temperature? Actually, we first have to find the data. So this is this another Word file here. So let me copy this. Let me copy here, and we can try the same thing, but at higher temperature. Okay. So first, let me open the data. Yeah, and let me see what I can get. So it's this thing. Before I do anything, let me check the value here. It's 41. Okay. So let us start similar analysis. Analysis, last used. Parameters. I will do such a thing. I will keep the constants. So 1.465 8 ER8. Let's keep it like that. It should be fixed. Here, something similar to the previous one, the correlation time. The next one should be fixed as well. The correlation time node. Then the next dipolar relaxation constant should be fixed as well, because there is no reason for it to change in time. Then this one should vary. And let's say, let's take it somewhat smaller, this thing. We got something. So again, it seems to me that we got very nice feed. Actually, what I have to say, if I would be doing it for myself, I just clearly see that I overestimated this frequency independent factor. Like 25 will be sufficient. However, you see, previously the correlation time was like 2.4. Now it's 2.2. So the dynamics is faster. Previously, the correlation time was like 4.8. Now it's more or less like 3. So the dynamics is faster. Previously, this correlation time was about 5, and now it's around 3. So this dynamics is also faster. So somehow keeping the dipolar relaxation constant temperature unchanged, we got a reasonable picture. Yeah, because each dynamical process became somewhat faster. So it makes some sense, I think.
Danuta, can I have a question?
Sure.
So you started with, maybe you already mentioned in the beginning, I missed, you started with 3 contribution. I mean, the higher number of contribution eventually will make it more difficult to interpret, especially in food systems. So can we, I mean, what would you recommend, like starting from 2 and increasing it, or just 3 will be a good point normally?
I think one never should go above 3. Because first is, you see, like people are saying that if you have sufficient number of parameters, you can fit whatever you like. So the credibility of the fit will be like, yeah. However, you can start with 3. And what happens? The software, how to say, is intelligent enough to decide. So for instance, if one of the contributions will be very small, you can always plot the contributions, yeah? And if it turns out that this green one, for instance, is just somewhere here, so you clearly see that it is not so important, this contribution. So then I would recommend to limit the fit to 2 of them.
Okay.
But first one should somehow see this picture.
Okay, just to understand the extent of the contribution of each.
Yes, because here it's not like I can remove one, yeah? It's somehow obvious. Because whatever frequency I take, really all of them are relevant. I mean, okay, you can say that in this frequency range, I could in principle neglect this one. Yeah, hardly, but let's assume that I could. However, then it must be consistent over the whole frequency range. So then I go here, and then I desperately need this component.
Okay.
Because those are of no, they are not relevant here, and so on. However, this approach really does not give us any deep insight into the mechanism of motion. But I wanted to show this to you because we still have time for the 3rd lecture, which I will use to feed some well-defined models for exactly those same samples.
Okay.
But then you will have a kind of comparison. But this is something what is always worth to do. If I may use the last 15 minutes, I would like to show you something else. Because as I said, I did not fit the data before. However, we have pectin profiles, which we actually collect now because we have the secondment, yeah? And now I'm wondering what happens, for instance, if we take one of the pectins. Because here, sorry, I lost the mouse. Because actually here, definitely we see water. Yeah, the relaxation, the water dynamics is much slowed down. However, taking into account the relaxation rates, it's still water. So let us take this one, for instance. Okay, so which one I need? Not this one, not that one. Okay, I want this thing. This one not, this one not, this one not. Okay, so I have one, yeah? this one. Let me change the frequency range, not just those y-axis. So you see this thing in more detail. Let me more or less read the last values. It's about 13, 14, because you see here we have clearly paramagnetic impurities. It does not go down. There's the contribution from paramagnetic impurities. And let me try to do exactly the same thing. And we see what happens. Analysis. So the old trick. I put here everywhere like that, because this is a kind of typical value. Here we had like 13. Let us keep it constant. And a slow process, which is usually of the order of -6, intermediate one. And sorry, I should have 13 here. And here I should have -8. Yeah, so a kind of typical input. At least did not create negative values, fit. Yeah. Again, the fit is very good. We'll see it in a second. Yeah, of course, it does not match the data here because paramagnetic impurities have this effect, so the relaxation goes up again, and we do not try to reproduce this now at this moment, yeah? However, beyond that, we have very nice data. So let me now look, and indeed it's like -6, -7, -8. So let us now decompose this thing into the individual contributions, and we'll see what happens. So analysis, last used, parameters. Okay. 0, 0, 0. 0, 0. And what I have here, 2.6, 1, 2, 3, 4, 5, 6. So you see this contribution is pretty small. 3.66, so this dipolar relaxation constant is pretty low, and 2.7 -6. 2.7 -6. Well, despite that, as the correlation time is quite long, this contribution is important. So you have, yeah, here the slow contribution. Let me now get next ones. Sorry. And what we had here. So it was 7.6, 1, 2, 3, 4, 5, 6. 7.6, 7.6 power 6. And here what we have, 538 -7. 538 -7. Simpson fit. Yep. This is what we somehow talked about previously, whether there would be a chance to get rid of such contribution. At this moment, we have it, yeah? It's not so small, this is the intermediate one. It's not so small, not so big, but this is something to think about what message said previously, that maybe one could attempt to have fit including only 2 contributions. But let us try further. Zero, 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 zero. Zero, and what we had here. 295.37. And what was the correlation time? 5:33. 5:33 minus 8. Minus 8 or minus 9? Something went wrong. Just a moment. You see, because we didn't see this contribution for a while. This contribution is very, very small. And for sure, this first one will be able to. This one will be just to be removed. However, here we still have, just a moment, workbook, and it was column. Column, set column values. It's 13. And this one is, yeah, window, yeah, insert, log to layer line. Apply, close, the same well-known thing. Let me change it. Yeah, so here you have this frequency independent term. Is absolutely sure. Looking at that this contribution is of no importance, yeah? This one. Okay. So let me see what happens. So I can do such a thing. Analysis and parameters. I can say this is 13, and we know this already. One contribution I will remove. So it's 0. And the other contributions were like, I don't know. Just let's say some initial parameters on the basis of the previous fit. Here it was like 8.6. And the fit was 5 minus 7. Well, it did not work good. because you see still we have this curve here. So the fit is not very good. However, it is largely probably because I fixed just this value here. So we can try again. This is something what happens although what I'm doing. Although in principle this contribution is not so small, but it matters. We can do such a thing: analysis, fitting, last used. Not, it's not what I wanted. Sorry. I will show you something. Analysis. We have to enter this dialog. Okay. It forgot everything. So analysis, fitting, nonlinear curve fit, open dialog, and I will do something funny. It's again user defined. It's this, parameters, and let me just copy those parameters. So I will have like 0, 0. Here I will have 13. Then what we have here is like 3.66. It will be funny. 3.66. 272 minus 6. 272 minus 6. Then I have 757. 757 is 6. I'm copying just those values, and I have 538 minus 7. 538 minus 7. Okay, what happens when I just remove those? I did something wrong, I suppose. But maybe it is so. Yeah, you see, this is indeed the reality. Look, I just plotted only those contributions without this one, this first one. And the deviations here are huge because this is logarithmic scale. So I somehow cannot get so easily out of that. This contribution is needed. So the best fit which I could get using only 2 contributions, let me make it like that. This will be the last attempt. Analysis, fitting. It's not so easy. So if I want to have only 2 contributions, I can make it like that. 5a6, 1a minus 6, 5e6, 1a minus 7. Yeah, so this is what you see here. With 2 parameters, this is maximum what you can get. So one clearly sees that one does not really capture the essential features, yeah? This fit is not sufficient. So we need 3 contributions. Well, so you have a kind of example. Let me remove that. How one could make a kind of parameterization of the data. And this you can do always, independently of the data, not going into what the motion is about. Such a trick one can do always. In the next time, in 2 weeks, I will use exactly the same data, but to fit, how to say, well-defined models, a kind of translation, motion, 3-dimensional, 2-dimensional. So it will be based, how to say, on reality. We'll go beyond parameterization, and then we could compare the parameters which we get from fitting some models to this, how to say, model-free way of reproducing the data. But as I said, it's a way of obtaining information which always works. So that's it for today.
Thank you very much.
Thanks.
Very helpful. So it was great to see step by step how the fitting.
I mean, maybe it was not very professional because, well, but if we do it together, there are not so many people is here, and if we are doing this together, it's maybe.
Yeah, and the video will be available, so people will have the chance to follow the steps later while they watch it afterwards. So
okay.
I think it's very valuable. Thank you so much.
Thanks.
Okay, so with this, we complete today's webinar, and we will have in 2 weeks our 3rd one. So hope to see you again. Thank you very much.
Okay, today I will